Okay, section 1.4, and I think this is finishing up paths. So a simple path does not cross itself. Except possibly at its ends. Now, more technically, so this is the intuitive idea. More technically, a simple path is 1-to-1. Okay, in other words, you could find an inverse of your function gamma of t. Okay, so gamma of t is invertible on that closed interval AB. Okay, so what can happen is, here is a simple path, but another simple path does allow you to get back to where you started. Okay, but not simple, so these are simple. Not simple would be something like a figure 8, okay, because it crossed itself. So that's a simple path, okay, and a path is closed if gamma of A equals gamma of B. In other words, it does, closed, oops, got slow there. Closed could either be, something like this, where it's a simple closed path, or it may not be simple. It may simply be closed, like the figure 8, and so that's closed. Okay, so it has to have no loose ends. Okay, so not closed would be something like that. Okay, so they mention that the unit circle C 0, 1. So that's centered at 0, radius 1, is typically a simple closed path. Now, I say typically because you would use something like, gamma of t is e to the it, 0 less than or equal to t less than or equal to 2 pi, or you might write it as gamma of t equals cosine of t plus I sine t, often 0 less than or equal to t less than or equal to 2 pi. Now you could use a different orientation, something like that, where you use like a negative, use the conjugate, something like that, cosine t minus I sine t, or e to negative IT, something like that. That would give a different orientation. You could use a different starting point, right? You could say gamma of t is e to the it, where you start at minus pi less than or equal to t less than or equal to pi. That would also be a simple closed path, okay? Not simple might be if you go around twice. So gamma of t equals e to the it, 0 less than or equal to t less than or equal to 4 pi. Okay, because I go around twice. And the funny thing is, right, it's not closed if, say, I did something like gamma, and not simple, but it's also not closed if I did something like e to the it and went from 0 less than or equal to t to 3 pi. Okay, because I wouldn't end up where I started. So it's not closed nor simple in that case. Okay, so finally, their last theorem here says if any 2 points in some subset of complex numbers can be connected by path in G, then G is connected. So when we first introduced connected, I started to say this sort of thing, but we didn't know what a path was yet, so I couldn't really say it that way. And then it points out that, you know, conversely, if G, subset of the complex plane, is open and connected, then any 2 points of G can be connected by a path in G and in fact we can connect them by a chain or a series of horizontal and vertical segments. Okay, so if we have this open set G that's connected, and I want to put these points in here, then this converse statement here says, oh, I can I can do it by doing some chain like that. Now I could also stair step it. I could go past and come back and come up that way. But those are all supposed to be straight lines. Now, why does it need to be open? Well, let's take a closed one, but in particular, I'm going to oops, I didn't want that because that's horizontal. that would work. So like that. Well, you know, if I want to connect this point to that point, I mean, this set is connected because I can connect this point over on the left to the point on the right. I just have to go through this line here to get there that's in the set. But there's no way to produce horizontal segments inside of G such that I can do it. Okay, so here's a case where, you know, this is a connected set, but it's not open. All right, and this says it needs to be open and connected. And then on the other hand, if I can, you know, connect any 2 points, then G is connected. And that really just comes from the definition of being connected. But I think that does it. That takes care of section 1.4.